How's everyone doing? Hope you all are doing okay today. Are there any questions before we get started? When was it? That was from last week. Okay. With other questions? Um, Take a picture and email it to me, or scan it and email it to me. That'll be the easiest. You can turn it in later today if you need to. Call it by midnight. Were there other questions? Alright, I think today we'll finish section 1.7. So last time, we started 1.7 last time. It's on solving quadratic equations. Um, and we're just continuing it this time. Okay. So we already talked about factoring as a method of solving quadratic equations. And the fact is that if we can factor it, that's generally one of the easier processes we could do, comparatively. Um, anyway, we're able to factor the polynomial or, the quadratic expression either by finding the greatest common factor and additionally sometimes factoring a trinomial into a pair of binomials multiplied together. And so, there are a couple of different ways we can do that. So we're going to look at the square root method, or square root property, I guess is what the book calls. The other books call it the square root method, but it achieves the same goal. And the idea here is that if we have an expression that is a perfect square, let's say that we have x squared on one side of the equation equal to some number, and I'm just going to call it a to represent some number. If we have that scenario, then we can take the square root of both sides of the equation, so we would do square root of x squared equals square root of a. Now, when we take the square root ourselves, like we are here, the other thing that we have to be sure to do is put a plus or minus sign in front of the number on the right-hand side. So we include a plus minus sign on the side with the number, since the solution could be positive or negative. The reason we say it's positive or negative, let me finish off this problem. So we would say x is equal to plus or minus the square root of a, whatever that happens to be for that given number. So the reason we say it could be positive or negative, let's look at a real example and illustrate that. So let's say x squared equals 9. We know that we can take the square root of both sides of the equation, sure to include a plus minus on the side with a 9. Square root of x squared is just x, and the square root of 9 is a number 3. As we know, the square root of 9 is 3, since 3 squared is 9. Now, not only is it true that 3 squared is 9, it's also true that negative 3 squared is 9 as well. As whether we take positive 3 times itself or negative 3 times itself, the result is still a positive 9. So going from here to here, that's why both of these solutions, the positive 3 and the negative 3, are possible. It's because when they are squared, they both become positive, if not already. Okay? Now the approach doesn't have to be as straightforward as that. That one's actually pretty simple. It could be that we have a little bit more complicated expression, and we can still apply the square root method. For instance, if we have 2x plus 1 squared equals 49, we start off by taking the square root of each side. Okay, and so we get 2x plus 1 equals plus or minus 7. Now, here's the dilemma that we run into. 2x plus 1 is equal to plus or minus 7. Now, plus or minus 7 counts as two different numbers. 7 and negative 7 are both unique. And so, what we have to do from here is we actually split it up into two different solutions. We let 2x plus 1 equals 7, and 2x plus 1 equals minus 7. Minus on the right. So either this expression is equal to a positive 7, or this expression is equal to a negative 7. And then we solve the equations individually from there. Now the steps that we use to solve these are actually identical for both parts, because the goal is to get x by itself. So subtract 1. So 2x is equal to 6. If we subtract 1 over here, we get 2x is negative 8. And then to solve for x, we divide by 2. I went too far. 2x, if we divide this one by 2, we just get x equals 3. And 2x equals negative 8. If we divide by 2 on both sides, x is equal to negative 4. Okay. Alright, so even though we had a little bit more complicated expression at the beginning, we are able to successfully factor and solve for x using our square root property as an alternative. Now, this problem, from what I've seen from a lot of students in the past, if I give you all 2x plus 1 squared equals 49, I see a lot of students, instead of taking the square root of both sides, which would be the easiest way to proceed, I've seen students that would take 2x plus 1 squared and expand that out, and then make it 2x plus 1 times 2x plus 1, FOIL that together, so it's equal to 49 on the right hand side still, and then subtract the 49 over, and then factor. Now, that's actually a valid approach. Okay. Um, Factoring will work in that scenario. So it is one option that we have if you prefer. I think the easiest way, though, definitely is just taking the square root of both sides and making it a simpler problem to begin with. Okay. Now, the alternative is, if you go that route with the squaring the binomial and then subtracting over so it's equal to 0 and then factoring is a nice alternative, but preferably we would realize that we can use the square root method here or square root property here, and it's a much easier approach. Okay. Now, of course, the book doesn't have any nice problems on this, where the number on the right is a perfect square, but that doesn't mean we can't work the problem. So 22, this is on page 58. B plus 4 squared is equal to 27. Okay. And so the idea holds true. I mean, we have a square expression on the left-hand side. Let's take the square root of both sides. Be careful when you draw your B's, it doesn't look like a 6. Mine looks a lot like a 6 right now. Okay. Anyway, so we know on the left-hand side the square and the square root are going to cancel. So it's just b plus 4. However, on the right-hand side, we have the square root of 27. 27 is not really a perfect square, so we can't take the exact square root of that, and I mean, we could. But we would, I mean, there's no whole number square root. I think that's what I'm getting at. 27 doesn't have a whole number square root, so we can't just write square root of 27 is blank. It's actually a complicated decimal value. Now, rather than doing that, because we don't want to do that if we don't have to, is there a way that we can simplify that expression? And I don't remember if we talked about it in this class or not. I think we did, but it might have been a while. Through 24, Jared. So even though we can't take a square root of 27, we can express 27 as 9 times 3, which means that the square root of 9 would become a 3, and then we'd still have the other 3 underneath the radical. I'm pretty sure we talked about that earlier in this semester, but as I said, it's been a while, and so if we don't recall, that's really what we're trying to do. Is we're trying to establish, is there a perfect square in this that will help us to at least simplify, even though we can't get the complete square root. And so we know 9 is a perfect square as a factor of 27. 27 can be written 9 times 3, and then the square root of 9 brings the 3 out, and the other 3 remains underneath. And so from here, if we subtract the 4, b is equal to negative 4 plus or minus 3 root 3. Now, again, one other thing that suddenly has come up. Anytime we have a plus minus expression, remember that counts as two different numbers, so anything we add or subtract over will have to go in front of that. We can't combine negative 4, well, we can't combine negative 4 with a radical term, regardless. There's not like terms. But even if this were a number, and we brought over that negative 4, we couldn't let negative 4 interact with this number because we're changing two numbers. One of them would be changed correctly, but the other would be changed incorrectly, and that's a problematic statement. So we always put, anytime we bring over a number, we always put it before the plus minus rather than after, just so that we maintain the accuracy of what this expression means. And again, what you may find is that you prefer to write it as two separate solutions, which is perfectly fine. In fact, you may or may not see the answers in the book, in the appendix of the book, say similar. So it depends on the textbook you read. Sometimes they write them separately. Sometimes they write it together as one expression. And I'm okay either way. But again, I'm not the one, grading your tests for this class, or for the other class. So. Okay. But that's the square root property, and it ends up being pretty handy as a means of solving a few types of problems a little bit more simply. Alright, the third method for solving that we look at, this one's the quadratic formula, which you probably are somewhat familiar with already. And the idea of the quadratic formula says if ax squared plus bx plus c is equal to 0. Notice that we do have this requirement that the quadratic equation is equal to 0. Okay? If it's not equal to 0, then the formula is not going to give us our accurate solution. So we have to make sure it's equal to 0 first. Then x equals negative b plus or minus the square root of b squared minus 4ac over 2 times a. Ignore that. Now, this solution actually comes from square root property being applied to this formula, but there's a little bit more to it than that. It's actually called a completing the square method that helps us do that. Hopefully we don't have to look at that, because that's way more difficult than any of these three methods. And honestly, the quadratic formula is the nice thing about the quadratic formula is that it does work for everything. So the burden here is on just doing the calculations properly. That was the main thing, really. Getting our order of operations correct, doing our calculations correctly, and then simplifying from there. So there's no upfront work for quadratic formulas beyond getting it into this format. It's just a matter of taking the coefficients, a, b, and c, whatever those happen to be, and plugging them in to each of their respective locations. Now, if we have, let's see, If we have, for example, let's see, 2x squared trying to think of a good factorable example with two minuses. This needs to be 2x squared minus 7x minus 15. Okay. Z or 2. I haven't written any z's yet. If I do write a z, I'll put a line through it, okay? And my 2's have this loop. Hopefully that helps. Alright, so we have 2x squared minus 7x minus 15 equals 0, and we want to use the quadratic formula to solve this. Now, this is actually a factorable expression, but from what I've noticed with my students in other classes, is that even though this is factorable, they actually really prefer using the quadratic formula to solve this because it's so much easier to use than to go through that process of factorization that we outlined there, or any other process of factorization. So for this particular equation, if you did prefer to factor it, you could, but at the same time, the quadratic formula is always an option. So a lot of students, when we have this number in front of x squared like we do here, anything besides 1 basically, a lot of them prefer to just use the quadratic formula, and that's okay if you do, and it's okay if you want to try to factor it first. But this does tend to be the faster way to the solution, I think. It does require a little more simplification, but I think most people are more confident in simplifying an expression than going through a process of guessing and checking potential solutions that we always end up trying to do with these trinomials when we try to factor them. So a equals 2, b equals minus 7, and c equals minus 15. Now, if it's a negative number, we want to make sure we include the minus sign. At the same time, notice we're not including the x's, we just want the numbers in front of them. Okay, so x equals, and we start off with minus b. Now, b is already negative, so changing the sign again would make that into a positive 7. B squared, that'll be negative 7 squared. Now, I'll come back to that actually, sorry. And then minus 4 times a, which is 2, and c, which is minus 15. And then the whole thing is divided by 2 times a. 2 times 2 would be 4 on the bottom. I'll just, since I'm not really simplifying anything yet, I'll just fill in 2 times 2 right now. We'll make it 4 the next step. Okay. One thing I wanted to point out is this square term right here. When we square whatever number is plugged in, that means we're multiplying it times itself. So negative 7 squared means negative 7 times negative 7, based on the order of operations implied here. Because the number itself is negative, we have to square the negative also because it's part of that number. So that means under the square root, we have 49. And then we have minus 4 times 8 times minus 15. So if we have minus 4 times 2, which is 8, minus 4 times 2 times minus 15, is that going to be positive or negative? Positive, right. So we have two negatives here, and that will multiply together to be a positive. Again, a common place where I see previous students make mistakes. A lot of it is just attention to detail, and that's really math classes in general. It's just attention to detail and how much we are able to keep up with those little pieces of detail and interpret everything properly from there. 4 times 2 is 8, and then 8 times 15 is 120, I believe. And then we have 4 on the bottom. And now it's really just a matter of simplifying this expression. Once we had everything plugged in, we don't need the quadratic formula anymore. We're just going to simplify under the square root and deal with that square root when we get to that point, and then try to simplify further if we can. So we add together 49 and 120, so it's 169. Now, when I say deal with the square root, one possibility is that the number underneath is a perfect square, so we can just take the square root of 169. It's 13. If this wasn't a perfect square, then we'd try to simplify it similar to how we did for an earlier problem that we worked where we had the square root of 27. I don't know if this is the one before this, but an earlier problem. And then once we take care of the square root, we see if there's anything else we can do with the rest of the terms. Now, we know 7 and 4 are not going to reduce, but in this case, because the square root of 169 comes out to be 13, so x equals 7 plus or minus 13 divided by 4. Because we're able to actually take the square root of that number and get rid of the square root, so we just have a plain 13, this one we'll want to go ahead and split up to two different solutions. 7 plus 13 over 4, and 7 minus 13 over 4. There you go. There we go. Sorry, the autofocus is sometimes slow. Mm-hmm. 5 and negative 1.5? I believe so. This is definitely 5, because 7 and 13 is 20 divided by 4, which, x equals 5. 7 minus 13 is negative 6 over 4. Yeah, that would be negative 1.5, correct. And we could write that as a decimal or a fraction. Either way is acceptable. If we need to do anything else with this number, I absolutely would recommend a decimal, because it's going to be much easier to take this 1.5 and plug it into some other function or equation than it would be for a negative 3 over 2 if we were to reduce this. Okay. All right. Let's see. Let's look at number 30. We're still on page 58. We have 2x squared plus 3 equals 8x. Now, what should we do first in this case? In order to be able to use the quadratic formula, there's one step that has to happen before all others. Look back at our quadratic formula there. We have ax squared plus bx squared plus c equals 0. Means that x equals negative b plus or minus square root of b squared minus 4ac over 2a. These are x's. Oh yeah, the problem has z's in it. I just write x's because it's easier. We could use either one, but whichever variable we use, it actually does not affect the outcome in the problem. So I find that most students like x better, just for consistency's sake. So I generally change them to x's, but sometimes I mix in the other letters just to make sure you all remember that we're not always going to be using the same letters. Anyway, the issue with this equation, the way it's presented to us initially, is that it's not equal to 0. And so in order to get it to equal 0, we need to subtract the 8x and put it over on the left-hand side. Now in this case, because 8x is the linear term, we would put it between the quadratic term and the constant. That way we have our standard order, x squared, x, and a constant. We want to be very specific about getting the order correct because that's how our coefficients for the quadratic formula are given to us, and they're in order. Okay? A is always the coefficient of x squared, which is 2. B is always the coefficient of x, in this case negative 8. And C is always the constant, which is 3 in this case. That doesn't ever change. Okay. So there's our quadratic formula once again, just for reference, for those of you that, I mean, some of you probably have it memorized already, but if you don't yet, that's okay. You probably have most of it memorized, but we preferably would want to make sure it's correct before we try to use it. So I tend to give you all the formula for this sort of thing. Alright, b is negative, so once again, negative b, just change this sign to a positive. Negative 8 squared, b squared, minus 4, a is 2, c is 3. And on the bottom, 2 times a is 2 in this case. So we got the numbers subbed in properly. Again, it's a matter of simplifying from here. Some of these steps, if we wanted to complete them as we entered the numbers, like if we saw negative 8 squared here, we could go ahead and just write this down as 64 instead of saying it's negative 8 squared. That will save us a step later on. Same thing on the bottom, we can just go ahead and make that a 4, it's no big deal. So negative 8 squared, 64. Now, notice that we only have the 1 minus here, so we'll stay negative this time. And we have 4 times 2, which is 8, times 3 is 24. And so we go ahead and combine those numbers under the radical. So we have a square root of 40 there. So 8 plus or minus square root of 40 divided by 4. Now we need to think of the 40 is not a perfect square, so we need to think of a way that we can split up 40 so it's a multiple of a perfect square and another number. Now as far as the perfect squares go, there's not a lot of them that are less than 40 to begin with. We have 1, 4, 9, 16, 25, and 36, and that's it. And of that group, it looks like 4 is going to be the one that works. 40 is equal to 4 times 10. So square root of 40 is square root of 4 times 10, and the square root of 4 is a 2, and then we still have 10 under the square root. And so we'll go ahead and change square root of 40 to 2 root 10. Whole thing divided by 4. And from this point, there's really 2 ways we can go from here. Generally, what we do is we go ahead and just divide both parts in the numerator by the 4 on the denominator. Okay. So we would do 8 divided by 4, and then we would do 2 divided by 4. Now, notice here, because these two have this square root connecting them, 2 times the square root of 10, that's all considered one term. So when we divide by 4, for one thing, we can only divide the number outside the radical by 4. But the second thing is that in some cases it's not going to be divisible. Like 2 divided by 4, we're not going to be able to do that because 4 doesn't divide into 2. We can still reduce that, absolutely, or we can change it to a decimal, but we won't be able to simply write that as a whole number anymore, unfortunately. So when we write our answer here, 8 divided by 4 plus or minus 2 square root of 10 divided by 4 . We would go ahead and go and make that a 2, 8 over 4, plus or minus, then 2 over 4 we can think of as 1/2 square root of 10. We could write 0.5 if we want to use a decimal instead. That would be perfectly fine in that case. But yeah, we do have a couple of options. Now, because we didn't get rid of the square root, we couldn't really break it down any further using that plus minus sign, unlike the last example. So it really, makes a difference what happens with this radical term. Since we can't get a perfect square, we can split it up into a perfect square times another number, 4 times 10, which gave us 2 root 10. Now, if this is a multiple of 4, we just divide 4 into both parts. It's great. Otherwise, we do have to create a situation here where it's either a decimal or a fraction. So we just go from there. How do you get 2 square root of 10? Oh, okay. Well, we said 40. 4 is one of the factors of 40, so you can think of 40 as 4 times 10. The reason I wanted the 4 specifically is because it is a perfect square and it's a factor of 40. Now, realistically, we would want, there's other ways to factor 40, but how should I say this? We want the factor of 40, factorization of 40, where the term that is a perfect square is as large as possible. So we want this 4 to be as large as possible. So if it were a 9 or 16, if those numbers divided evenly into 40, we would certainly want to use those. 4 is the largest number that goes into 40. That is also a perfect square. And so we set up 40 equals 4 times 10, took the square root of both sides of the equation, and then the square root of 4, we can bring it outside as a 2. Square root of 4 is 2. And the square root of 10, we can't simplify any further, so we'll just leave it square root of 10. Good. Good. I also wanted to look at 38. We have 5 minus 4 over k minus 1 over k squared equals 0. I don't know if we covered this. Is this something I skipped? Looks like 1.4. Yeah, it's all about 1.4. I don't know that we'll need to do this problem necessarily, since we did skip 1.4. It was not in my instructions as far as what I needed to present this semester, so it may be that we just don't need it. But a problem like this, even though it doesn't look quadratic, it's actually a rational function or rational equation. And what we mean by rational is that it can be written as a fraction. Basically, it has fractions. So, when we I lost track. Sorry. Um, this is, I said, this doesn't look quadratic, but it will be after you multiply by the common denominator. And I think that's what I was leading up to. The common denominator in this case is k squared. So what we would do is multiply all three of our terms here by k squared. And technically, we also multiply the 0 on the right by k squared. It just doesn't achieve anything. Anything times 0 is still 0. Okay. So we distributed k squared to all three parts, or all four parts. So you get 5 times k squared, 4 times k squared divided by k is still on the bottom there, and then k squared over k squared. We multiply a fraction by a term. This term k squared always multiplies the numerator. That's why I put 4k squared and 1 times k squared, or just k squared. Now we can reduce these. K squared divided by k, we know that's 4k, and k squared divided by k squared will be a 1. Alright, so we have a equals 5, b equals minus 4, and c equals minus 1. One thing we noticed in this case, the variable is actually k, not x. So instead of saying x equal, we should say k equals. But that right there is just our formula. And you don't have to write it down like that, as long as you know what it is. Now we take negative b, so b is already negative 4, so another negative would make that a positive. Basically, think of it as the opposite of b. That might be an easier way to go with that. So 4 plus or minus negative 4 squared minus 4 times a, 5, times c, minus 1. And 2 times a, 2 times 5, which is 10 on the bottom. Alright, what does this work out to be under the radical? Negative 4 squared minus 4 times 5 times minus 1. How does that simplify? +20. Good. Yeah, we definitely get a 16 here when we square the negative 4. And then minus 4 times 5 times negative 1. So minus, and this will be a negative, so that'll be a plus. 4 times 5 times 1 is 20 times 1, or 20. Does the 4 have to be a negative 4? Oh, this one in front, Brenda? Is that what you mean? Yes, okay. The reason, let me make sure I wrote the problem down correctly. Yes. The reason that this will be a positive 4 is because b is negative 4 here. But then we want the negative b, or the opposite of b, to be plugged in. So the opposite of negative 4 would turn that into a positive 4. Okay. Alright. So, this will be 16 plus 20, that'll be 36. And that's where we're at. Can we take the square root of 36? And it turns out, yes, square root of 36 is a 6. Okay. Now, because we were able to take the square root and get rid of the radical completely, it's just a plain 6 right there. Now we'll branch it off into two solutions. 4 plus 6 divided by 10, and 4 minus 6 divided by 10. So this will be 10 over 10. So we get a value of 1. K equals 1. And over here, 4 minus 6 is negative 2 divided by 10. And so negative 2 over 10 is negative 0.2, right? Yeah. Okay. Oh, sorry. And again, we could write that as negative 1 over 5 if we'd like, but negative 0.2 is just as good. This looks horrible. There's some quadratic formula problems they've given us with decimal problems in the textbook, or decimal coefficients where a, b, and c are all decimal values that we plug in. Really calculator heavy. I probably should make us do it, but I don't want to. Alright, let's look at a couple of these applications. let's start with 62 on page 58. Oh, I'm sorry, but am I in the right place, or is there something else that you need? Okay. Let's see, so I said 62. Not page 62, number 62. It's page 59, which is pretty close to the same thing. Okay. A landscape architect has included a rectangular flower bed measuring 9 feet by 5 feet in her plans for a new building. She wants to use 2 colors of flowers in the bed, one in the corner and the others for a border of the same width on all sides. If she can get enough plants, just enough plants, to cover 24 square feet for the border, how wide can the border be? Alright, let's figure this out. Landscape architect has included a rectangular flower bed measuring 9 feet by 5 feet. So we have a flower bed that is 9 feet by 5 feet. And it is rectangular. Right. What else do we have here? She wants to use 2 colors of flowers in the bed, one in the center and one for a border of the same width on all sides. She can get just enough plants to cover 24 square feet for the border. How wide would the border be? So we have 24 square feet of border. Okay, so I think that's the key details right there. And so the concept is we have a situation like this. Where we have a flower bed in here. And we have a border going around. Now the flower bed is 9 feet by 5 feet. And we have this border part should account for 24 square feet. So now let's say this is X. And so this should be an equal value X here. The border is going to be the same width all the way around. So the distance from the flower bed to the edge of the border is the same value on all sides. So that's X. And that's X. Okay. So if we look, going all the way across, we have X, we have 5, and we have another X. So this side is 5 plus 2x. What about the vertical side? Well, we just add these together. So x plus 9 plus x, that means we have 2x and a 9. So we can say 9 plus 2x or 2x plus 9. The order is flexible. Generally, we should put, I don't know. We could put the x first, but... Oh, excuse me. Alright, so our width is 5 plus 2x, our length is 9 plus 2x, and for the area of the triangle, the area of the triangle is the product of length times width. Or, sorry, rectangle. Sorry. The area of a rectangle is length times width, so that's what we can apply there. Okay. So our length times width in this case is 5 plus 2x. Times 9 plus 2x. 5 plus 2x times 9 plus 2x. And that equals the area. Now, let's think about the total area of this enclosed flower bed. We know we have 24 square feet of border that we would like to use all of, so this entire outer part is 24 square feet. Now the inside part is our original flower bed, which is 9 times 5, that's 45 square feet. So we have 24 square feet on the outside, plus 45. And that comes out to be 69 square feet. Even though we don't exactly know how wide the border is, we know how much there is of that. So it's 24 square feet of border, and 9 times 5, so 45 square feet inside the picture. Giving us a total of 69 square feet. It's kind of hoping for a more even number, preferably a multiple of 4. But I guess it's not going to happen. Yeah, that's gotta be. It's gotta be 69. Okay, so we'll take this number and we'll put it over here where the area is. Well, it wouldn't be too bad. Once we move it over, it's not gonna be too bad. Sorry. Now we're getting a little carried away. We do have to FOIL these two binomials together. And so we'll take 5 times 9, 5 times 2x. 2x times 9, 2x is 2x, 5 times 2x is 10x, 5 times 9 is 45. 9. I got 9 times 5. 9 times 2x is 18x. And 2x times 2x is 4x squared. Okay, let's combine our like terms and then move our 69 over to the left hand side. So, and also at the same time we want to make sure our highest exponent term is first, so we put 4x squared first, then whatever x we have, this looks like 28x, and then minus 45. What am I doing here? Sorry, plus 45. Let's get ahead of myself with the subtraction. So we'll subtract the 69 over. Okay. So it'll be 4x squared plus 28x. This will be 45 minus 29, which is minus 24 as a constant there. And this will be 0 on the right-hand side. So let's see, we have 4x squared plus 28x minus 24 equals 0. And so we look at that expression. Is there a common factor that we can take out? For x. Remember, we can only take out something from if all three terms have that in common. We definitely can take a 4 out, because all three of these numbers are multiples of 4. But just 4, yeah. The reason we don't want to do x is because there is no x in this third term. If it was just the first two terms, we could absolutely take out 4x. That'd be the common or least common multiple there. We don't want to do that with 24 though, because there is no x there to begin with. Okay, and so if we go ahead and divide those, sorry, they equal 0. We have x squared plus 7x minus 6 equals 0. Don't know if that's factorable. It's not factorable. Now, to solve, we look at that, and it looks like something that should be factorable. But if we think about the numbers that multiply to -6, and whether if there is a way to get a sum of 7 between a pair of those terms, it turns out we can't get a positive 7. because even if we use a negative 6 and a positive 1, that would still be just negative 5, or if we use positive 6 and negative 1, that would be a positive 5, but it wouldn't be positive 7. And so there really is no factorization for this trinomial. Now, we'll use a equals 1, b equals 7, and c equals negative 6. Notice we're completely ignoring the 4 on the outside. Anytime we can factor out a constant, we only want to work with the constants left inside, because it should still give us the correct answer. And because we got rid of the 4 by factoring out, it makes the calculations a lot easier when we get into the quadratic formula. So negative b would be negative 7. B squared would be 1 squared, or sorry, actually be 7 squared, minus 4 times a, 1, times c, minus 6. And on the bottom, 2 times a is 2. So that gets everything plugged into the quadratic formula. And so let's go ahead and simplify everything under the square root. We know 7 squared is 49. What about the rest of it? Positive 24. Okay. And so we add those together. So 49 and 24, I believe that's 73. And so finally, with negative 7 plus or minus the square root of 79, or 79 over 2, we look at that and we say, can we, well, first of all, is 79 a perfect square? And it turns out it's not. 81 is a perfect square, it's 9 times 9. And then below that, 64 is a perfect square, but 79 falls in between them. So 79 is not a perfect square. And then, since it's not a perfect square, we try to see if we can factor it anyway. And we think about the factors of 79, and are there any 2 that we can use to help us reduce the expression further? And so, it turns out 79 is what we call a prime number, because the only factors that it has is technically 1 times 79, which we call the trivial factorization, because we always know that 1 times a number is equal to that number. And the end result here is that we cannot separate this square root any further. It cannot simplify it at all. Therefore, we can't simplify what's around it. So that's our answer right there. Okay. Yes, 73. I was looking at that and something's off. And I wasn't thinking of it, so I just moved forward. But either way, 73, the same argument holds true. It's a prime number, and therefore it's only factorable by 1 times 73 in this case. Yeah. Any questions there? How the heck this is... I'm trying to, I don't think we made a mistake. This is a really bizarre flower bed, though, if we didn't get a whole number answer here. Remember, we're still on the flower garden problem. Here's the thing that we run into. If we have our formula here, we could branch it off into two solutions. -7 plus root 73 divided by 2, and -7 minus root 73 divided by 2. And we can calculate those on the calculator. So -7 plus the square root of 73 divided by 2 gives us a 0.772 for our first solution. And for the second one, we get -7 minus the square root of 73. And then divide it by 2. And we got -7.772. Now, if x is the, going back to our picture here, x is the width of the border in feet. Is it possible for this width to be a negative number? No. It's not realistic to say that a flower bed or component of a flower bed is -7.772 feet wide. It doesn't make any sense with it being negative. So we can rule out the -7.772 as a valid solution. It's not going to be valid to this problem. And so we're going to go ahead and say x is 0.772 meters. And actually, not meters. In the problem, they've actually given us the data as feet, so we want to make sure we use the identical units here. Does that work out anything? Probably not. No. Okay. So we get 0.772 feet. So that means the garden flower bed has a border that is 0.772 feet wide. So a little bit over 9 1/4, it turns out. Sorry, 9.3 inches, basically. Okay, so that's how wide we'd want to make our flower bed there on the border, just to enclose the region inside perfectly. Alright, I was going to give you one of those for homework. That one turned out terrible, though, and I don't want to put y'all through that on your own. So I'll just give you a few quadratic formula problems, and then the square root property problems, and I think that'll be good. Okay. So we're on page 58. Go ahead and look at 21 and 23. Let's do 25, 29, 35. I think that'll be good. That'll be good right there. What is next Monday? 2nd? 5 days to the month? Yeah. Monday, November 2nd. That one should be a lot shorter and a lot easier than the other two, so that'll be good news, hopefully. Do you all have any questions? Okay. So let's go ahead and stop right there. And you'll have a good rest of the day. Stay warm. It's pretty cold right now, actually. Tomorrow's gonna be even colder. But yeah, have a good day, and I'll see you all again on Wednesday.